March 1979. Somewhere beneath the Arctic Ocean, American sonar operators are staring at something that makes no sense. They're tracking a submarine, but the numbers coming back don't add up. At first they think it's a malfunction, a calibration error, maybe a torpedo that was fired and never reported. Because what they're looking at is moving at 41 knots, deep underwater, sustained and deliberate. That's 47 miles an hour beneath the surface of the ocean. And that mattered for one very specific reason. It was faster than the torpedoes America would use to destroy it. Within hours, intelligence reports were crossing desks in Washington. The Soviet Union had built something that broke the fundamental rules of submarine warfare. Not a vessel you could hunt, a vessel that could hunt you and survive anything you threw back at it. The $2 billion submarine that could outrun torpedoes. To understand what the Soviet Union was trying to do, you first need to understand what they were up against. By the early 1960s, the United States Navy had developed something that bordered on a superpower in its own right. An underwater fleet so quiet it had effectively vanished from the ocean. This wasn't an accident. Over the previous decade, American naval engineers had systematically attacked every source of noise their submarines produced. Machinery was mounted on dampening systems that absorbed vibration before it could travel through the hull. Reduction gears were machined to tolerances that hadn't existed a decade earlier. Propellers were cast with such precision that they barely disturbed the water around them. The result was a fleet of submarines that could follow a Soviet vessel for days, positioning themselves for a kill shot, and never once be detected. For Soviet crews, it was the opposite experience entirely. American submarines had simply ceased to exist. They'd been there, and then they weren't. And in their place was an uncomfortable silence that carried a very clear message. If a war began tomorrow, Soviet submarines would be destroyed before they had any chance to retaliate. Soviet military planners understood exactly what they were looking at. In every metric that mattered, acoustic signature, crew training, stealth technology, they were somewhere between 5 and 10 years behind. They had tried to compensate with numbers, flooding the oceans with more submarines than the Americans could possibly track. But quantity hadn't worked either. American vessels were sinking Soviet contacts in training exercises without ever breaking cover. And the Soviets knew it, so they faced a choice that every nation eventually faces when they find themselves losing a race they cannot win. Keep trying to catch up or change the rules entirely. In 1960, a Soviet naval engineer named Mikhail Rusanov proposed something that his contemporaries found almost absurd. He argued that the Soviet Union should stop trying to build quiet submarines altogether. Instead, they should build a submarine that was so fast, so deep diving, and so structurally lethal that being detected was irrelevant. By the time an enemy crew had processed what they were looking at, the submarine would already be gone, or already attacking. The analogy Rusanov had in mind was the MiG-25 Foxbat, the Soviet interceptor jet that the West had spent enormous resources trying to understand. A machine that responded to the threat of missiles not by evading them, but by simply flying faster than they could follow. He wanted to build that logic into a submarine, something that didn't hide from weapons, something that outran them. The design that emerged from Project 705 was unlike anything Soviet shipyards had attempted. Every inch of the exterior was smoothed over to minimize drag. The bow planes, the horizontal fins used to control dive angle, were made fully retractable at high speed so they wouldn't slow the vessel down. The internal crew was reduced to just 31 men, less than a third of a standard attack submarine, because most of the systems a crew would normally operate were going to be managed by computer. Automated ballast systems, automated torpedo loading, a centralized command suite that integrated navigation, sonar, and targeting into one interface. For the Soviet Navy of the 1960s, this was a fundamental conceptual leap. But none of it would matter without the hull, because the hull was where everything became truly extraordinary and truly dangerous. Standard naval steel wasn't going to work. The vessel needed to be lighter and stronger than anything that had ever been built. So Soviet engineers decided on titanium. And here is where the story gets complicated, because titanium at industrial scale is one of the most difficult materials on Earth to work with. The problem is atmospheric oxygen. When titanium is welded and exposed to even trace amounts of oxygen at high temperature, the seams become brittle. Under the crushing pressure of deep water, a brittle seam fails, which means the submarine implodes. To solve this, the Soviet military constructed enormous sealed fabrication bays, pressurized entirely with inert argon gas, essentially the same environment you'd need to build a spacecraft. Workers inside had to wear independent life support systems because the air around them had been completely replaced. The entire titanium hull of a nuclear submarine, welded by men in diving suits, breathing through external oxygen lines, inside a factory that had been turned into a vacuum chamber. The fact that it worked at all is one of the more remarkable industrial achievements of the Cold War. At the heart of the vessel sat something equally unconventional. Rather than the pressurized water reactors used in every other submarine in the world, Project 705 used a liquid metal core, a reactor cooled by a molten alloy of lead and bismuth. The physics of why this mattered come down to one thing: temperature. Lead bismuth doesn't boil until 1670 degrees Celsius, so the reactor could operate at extreme thermal thresholds without any risk of a steam explosion. That meant no massive, heavy pressure vessels. The entire core could be built compact. And because liquid metal transfers heat almost instantaneously, throttle response was unlike anything else afloat. The submarine could accelerate from a dead stop to 45 knots in under 60 seconds, a figure that, even now, is difficult to fully absorb. When the CIA compiled its assessment of Project 705, cross-referencing satellite imagery from the Leningrad shipyards with the acoustic telemetry gathered in March 1979, the report that landed at the Pentagon contained a problem that had no clean solution. The United States Navy's primary anti-submarine weapon at the time was the Mark 48 torpedo. It was capable of roughly 40 to 45 knots. It had an operational depth ceiling of around 400 meters. The Alfa-class operated at 45 knots and could dive to 700 meters, which meant that if an American submarine fired a Mark 48 at an Alpha from astern, and the Soviet crew simply applied full throttle and went deep, the torpedo could not catch them. It would chase the vessel until its fuel ran out. A weapon system that had taken years and billions of dollars to develop had just become tactically useless against a specific class of enemy. The response across NATO was immediate and expensive. The United States accelerated the Mark 48 ADCAP program, the Advanced Capability Variant engineered specifically to push past 55 knots at much greater depths. Britain went further, developing the Spearfish torpedo with a gas turbine engine capable of over 60 knots, designed specifically to have enough speed margin to run down a titanium-hulled Soviet submarine at depth. The requirements for the next generation of American attack submarines, what eventually became the Seawolf-class, were revised to account for an enemy that could dive deeper and accelerate faster than anything previously wargamed. 7 submarines had forced the world's most powerful navy to redesign its weapons, rethink its doctrine, and commission an entirely new class of attack boat. By that measure alone, Project 705 had achieved something extraordinary. But there was something the dossiers and intelligence assessments couldn't fully capture: the experience of actually operating one of these submarines. Because the same property that made the liquid metal reactor so powerful was also the property that made it almost impossible to live with. The lead bismuth coolant froze at 125 degrees Celsius, not cold, not room temperature. 125 degrees, which meant the reactor could never be switched off. Not in port, not during maintenance, not during the months a submarine sat idle at the dock. The core had to be kept continuously hot, which meant shoreside heating infrastructure had to pump heat through the hull at all times, which meant the submarine was never truly at rest and never truly in the care of her engineers, because you cannot conduct serious maintenance on a reactor you cannot turn off. In the remote naval bases of the Kola Peninsula, that infrastructure was fragile. Steam lines fractured in winter storms, power supplies cut out, and when they did, the countdown began immediately. Because the moment the coolant temperature dropped below that threshold, the liquid metal didn't just cool. It crystallized, it expanded, it ruptured the internal piping, locked the fuel assemblies in place, and turned the most sophisticated nuclear reactor the Soviet Navy had ever built into a solid, radioactive block of metal that could not be repaired. One submarine was lost this way while sitting at the dock, not in combat, not on patrol. While moored, the entire vessel had to be decommissioned and cut apart. Of the 30 submarines originally planned, only 7 were ever completed. Each one had cost approximately twice what a conventional nuclear submarine would have required. The titanium alone had forced the Soviet Union to develop an entirely new industrial sector, new fabrication methods, new tooling, a new workforce, for a fleet that never materialized. And the vessels that did exist spent more time in maintenance than they did at sea. Project 705 didn't fail because the engineering was wrong. The engineering was extraordinary. It failed because the Soviet Union built a machine that required a world around it that didn't exist yet, infrastructure it couldn't sustain, an industrial base it couldn't scale, and an economy that couldn't absorb the cost of doing it again. But the fingerprints of what Rusanov designed are still visible in the vessels that came after it. The titanium fabrication techniques developed for Project 705 directly enabled the Sierra and Aquila classes that followed. The automated command systems pioneered in its centralized control capsule established the reduced crew sizes that define modern Russian attack submarines today. The Alfa-class wasn't a failure that the Soviet Navy quietly buried. It was a laboratory, the most expensive and dangerous laboratory in the history of underwater warfare, and everything that came out of it was used. In March 1979, American sonar operators tracked a contact they couldn't explain, A submarine moving at speeds that should have been impossible, doing something no vessel had ever done before. They were right to be afraid of it. What they couldn't have known, what the Soviets themselves were only beginning to understand, was that the most dangerous thing about that submarine wasn't how fast it could move. It was what it would leave behind after it was gone.